Hello, this is T Chapman 500 bringing you an update to my 16-bit microcontroller project. I was intending to make a video as a series of time-lapses to show you the development of the processor, but something happened and I won't be able to do that. Instead, I'll be making update videos occasionally showing the progress that has been made on this project and explaining the new components that were added since the last video. Let's start with the instruction pipeline. In this processor, instructions take at least 2 clock cycles to execute, including the clock cycle needed to load the instruction into the instruction register. The instruction pipeline allows an instruction to be loaded into the instruction register while the previous instruction is executing. It allows multiple instructions to be executed at the same time, but be in different stages of execution. This instruction pipeline will have 4 stages. Each stage of the pipeline starts with a register to store the instruction data in, and ends at the register of the next stage. Each stage, except for the first stage, will generate control signals specific to that instruction. The first stage of the instruction pipeline will load and decode the instruction. For most instructions, no control signals will be generated at this stage. Instead, it will load the next instruction into the instruction register, decode the instruction, and pass the decoded instruction into the next stage. Some instructions, like the jump or call instructions, will generate control signals at this stage to block the loading of new instructions. At the top of this circuit, I have 4 decoders, each of which decodes 4 bits of the instruction that is loaded into the instruction register. The 2 decoders on the left work on the opcode, while the other 2 work on the operands, which often contain extra data for the loaded instruction. Other times, the operands hold the address of the register in the register file where the data is to be used, read from, or stored to. Immediately to the right of the decoders and below them are several columns of logic gates that take one signal from each of the 4 decoders and produces a decoded instruction. Most instructions only take signals from 2 or 3 of the decoders, with the rightmost decoder results being ignored. The program counter stores the address of the next instruction that will be loaded into the instruction pipeline. Previously, this component was shown to have 2 outputs, the current value and the current value plus 1. I have removed the second output from the program counter because it will never be needed. The original plan was to stop the program counter during call instructions, which would have needed that second output so that the return address could be stored on the stack. But I changed my mind and decided to keep the program counter running while the call instruction was being processed until it reaches the return address. The register file originally was shown to have 32 registers, with the stack pointer being hardwired into register 31. Since then, I have decided that the instructions will have 4-bit operands instead of 5-bit operands, requiring me to reduce the register count to 16, which is what you see here. The stack pointer is now register 15. The register file has 3 address inputs, 1 address for each of the data outputs and 1 address for the data input. These fields specify the register that data is to come from or go to. Each register has a unique address, and there are enough registers to use up all of the available addresses. There are 2 temporary registers in this circuit so far. These registers cannot be accessed through software, but are used by specific instructions so that the register file remains free for the software to use. Data that is loaded into these registers is only considered valid for the instruction that loaded the registers. The address register stores the immediate address of a load or store instruction and is a pointer to the location in RAM or the program memory where the data is to be loaded from or stored to. This address can be added to an address in the register file in order to serve as an offset from the base address stored in the register file. The jump register is loaded whenever a call or jump instruction is loaded into the instruction register. This register will hold the address of the next instruction to be executed while the program counter is being saved to the stack or the jump condition is being checked. When a call instruction is loaded, then the jump register will store the address of the function being called while the program counter is incremented to the return address and then pushed to the top of the stack. When a jump instruction is called, the jump register will store the address of the next instruction to execute should the jump instruction evaluate to true. While the jump condition is being evaluated, the instruction register continues to be loaded. If the jump condition evaluates to false, then the jump register is not loaded into the program counter, and the next instruction in the pipeline is executed. If the jump condition evaluates to true, then the instruction pipeline is cleared and the jump register is loaded into the program counter. In the next part of this series, I intend to have at least the second stage of the pipeline completed, as well as the arithmetic logic unit, the multiplier, and the divider in place. Also, this is my first fully scripted video for this channel and would like some feedback on this new format. Hopefully, future videos will be longer than this one. If you enjoyed the video and found it informative, then don't forget to rate, comment, subscribe, and share. This is T. Chapman 500 signing off.